All right, here we go. Hey, folks, thanks for coming up. My name's Sam Hallam. I'm a senior data engineer at Reverb. Reverb is the world's largest online marketplace for used and new musical equipment. If you've ever looked and bought a guitar online, you've probably interacted with us in some way. This talk is going to be about the data engineering team and how our role is sort of transitioned into becoming a machine learning operations team. We built out an ML platform that involves Ray and Anyscale kind of really at its core. And while the data engineering team is not a machine learning operations team, we've really been forced into that role over time as the nature of our organization. So before we began with Ray and Anyscale, we had an existing platform. We had some vendor tooling. We had some existing models, which worked okay, maybe, but not really. And some legacy infrastructure that was really expensive, cumbersome, and just really a pain to maintain. And of the existing teams, data engineering and data science were closest to the space, so that's where we started. Obviously, data science, we're focused on model development and amongst many other things, and the data engineering team is focused on access to the data, infrastructure, and deployment. And so very quickly, the data engineering team has also become the machine learning operations team. And before I go on, I should say these teams aren't very big. I'm talking fewer than 10 engineers on each team in our case. And so this is what our rough model development process looked like. In the beginning, data science and data engineering were very siloed. We didn't really collaborate much at all in the process. And really, that kind of made sense to us, right? Data scientists know things about model development. They know things about tweaking hyperparameters, selecting features, and data engineers certainly don't, or I certainly don't. And so what would then happen is this would kind of move along to data engineers for productionalization. We'd get a model that we didn't really know what it did, we didn't really know what it was for, but we had to put it into production. And of course, that fell really flat. We had to go back and talk to the data science team. We had to ask them, oh, what are you using this for? What kind of resource requirements do you need? What kind of data is this model going to interact with? And this was a problem because data engineers are not machine learning engineers. We're not always equipped to handle this stuff. There's a lot of frameworks that are really hard and confusing. If, like me, you write a bunch of Python, Airflow, and SQL pipelines, and you're good with your life. One example I can think of is PyTorch, right? There's so many parameters in there to optimize. One thing we had was early stopping hyperparameters. You can tweak those, make the model run faster, finish training earlier, but then you lose a ton of efficacy in the model. I did that one, that's me. And so transitioning the model prototypes from notebooks into production code led to a real loss of model fidelity for us. And in addition to that, assessing the performance of the models themselves and monitoring drift, those aren't really common data engineering domains at all. And so we began with Ray and Anyscale, migrating from an AutoML platform that was pretty unsatisfactory. We quickly needed to put models into production much faster than before, and we needed every single engineer and data scientist and anyone who was touching model code at Reverb to be able to interact with this. And so this pattern we had, this research repository that we had developed, it just really wasn't an ideal state. We wanted everyone to be a part of this. And so I mentioned this a couple of slides ago, and I want to talk about this word productionalization before we move on. What does it mean to productionalize something? There's sort of a mental model you can have in your head, I guess, of like a conveyor belt. Model starts being sort of crafted out of clay. You need to change it frequently. You need to get things together before you make it's ready to go, and you make like 1,000 copies of it in the future. But pretty quickly that fell flat. We had to go back, talk to model creators, and also educate on, say, hey, if you do it this way, this is going to need to be rewritten so much more later on down the line. This still isn't really a solved problem for us, but we've made a lot of steps towards solving this, and we no longer have to do really large rewrites later on in the process. And so in a way, data engineers can be ML engineers. We're used to composable, dependable, accurate data pipelines. That's a key part of both data and ML engineering. And we often support production services that deliver data to user-facing applications. with all the monitoring and observability tooling that kind of comes along with that. And when we're able to bring software engineering best practices earlier in the model development cycle, we get higher quality code from the start, and a shared understanding of what's needed for the business by all engineers. So now I'm going to talk a little bit about our ML development process at Reverb and a little bit about the platform that we've built over time. So here's a quick example of our ML repository. We use a monorepo for all of our Anyscale Ray workloads. I've been at a couple of talks here over the last couple of days. It seems like it's a really common pattern. And for us, we divide this monorepo into projects. And so one project, which is distinct from an Anyscale project, but one project for us is a Python virtual environment that includes all related Ray jobs and services and whatever other ancillary code we need that to run on. We use Poetry for local development and local environment management, and also on Docker containers when they're running in production. So as part of this repository, we have a CI/CD pipeline that pushes Docker images to our own ECR repo that those Anyscale jobs and services are run on. This same CI/CD pipeline also uploads configurations to S3, which we pull down from Airflow, which we use when we're triggering the workloads themselves. And so I mentioned in the previous slide, we use Airflow for job orchestration. We also make a lot of use of dbt for data transformation. And we support all data consumers at Reverb using these tools, not just for ML purposes. And so this pattern that we have, where we use Airflow to trigger dbt jobs that transform data, we export that data into S3, and then we trigger a workload with that S3 path as a parameter on the Anyscale job, is something that works really well for us. It helps avoiding siloing data pipelines, and maybe more importantly, it helps us avoid these bespoke training data sets that can sometimes appear out of nowhere. Trains beautifully, is a perfect representation of the data, except we have no idea where it came from, and we have no idea how to put it back together again. But having said that, these pipelines are often built, post-hoc. They're built after the fact. They allow for changing data during model development. Again, this assembly line model sort of starts to fall apart here. Often we have to go back. We find a model is trained well, but maybe it takes too long. Maybe it's too expensive. Maybe the compute is too heavy for what we need. So we go back, we change it, we reduce the number of features, and so on. Now for local development, we've got a couple of in-house CLI tools that we've put together. Again, just a simple script built into Poetry for every single project of ours. So we're able to submit a job to our Anyscale cluster, and as parameters, we can specify the compute config we need, the Docker image URI we want, input data, and any other parameters that might be job specific. So this is accessible to anyone who has access to this repo. And more importantly, it kind of encourages best practices early on, because your code actually has to run on Anyscale. This is no longer a model that can run partially or train a little bit. This has to be kind of mostly an end-to-end application. And so this, we found, really encourages sort of best coding practices right from the get-go. We do something very similar for our services, except instead of so many parameters, we just have a YAML config file that contains all of that business. And so talking a little bit about Raceserve, we like Raceserve a lot. It works really well. We love being able to scale models independently. We love having separate environments and good testing. The Canary rollouts are great on Anyscale. It's just a big part of what we do. For some search models, we also use a Redis-backed feature store to pull down features really quickly and try to get as low-level inference as possible. And most of our services that are Anyscale services are actually proxied through by one of Reverb's own services. So we use that to handle any of the actual business logic as we retrieve data from the request. Nowadays, we've gotten to a point where some of our teams are big, sophisticated in the ideas. The models they're developing are fairly sophisticated. And so consulting with us on what resource requirements they might need or how they need to get this thing working is a back and forth process. We don't have all the answers anymore. But our processes are pretty good, and most teams kind of get what they need to get things moving. So for monitoring, we use Vector to export our Anyscale job and service metrics and logs to our observability tooling. We're really big fans of Vector at Reverb, and actually we're trying to think of other ways we can use it. It's a really flexible tool. But from here, we do the usual things. We monitor traces, we set alerts for missing, erroneous data. We've got user-facing dashboards for ad hoc analysis. One thing for us that's still not all the way there is monitoring the actual quality of a training job run. Things such as a poor training run or measuring drift, we don't always catch that today, but it's something we're chasing down and really trying to close the gap on. And so here's kind of the conclusion I have after all of this. Data engineers maybe should be ML engineers, or certainly MLOps engineers, right? Expanding the scope of data engineering to include machine learning operations, it's kind of a natural thing. It kind of makes a lot of sense. And at Reverb, the data engineering team has learned a ton. We've learned a ton about how models work, how they're best deployed. This also goes for the entire broader engineering organization, as we brought everyone in to learn these same things that we've learned. So as a company, as an engineering organization, we've got much better at transferring skills over. In addition to all that, these models have helped us lower costs from our previous solutions, sped up delivery time, and we've had a much larger swath of the engineering org able to contribute. And so that's really it. We've got a lot to learn. We're still working on things. There's still things we'd wish we'd done differently, but we're really proud of our platform. It's really helped us get where we need to be as a company and really helped us make the world more musical. That's it for today. Thanks so much.